Okay, so this rolls back a little bit from where we left off in the last lecture, but we can calculate enthalpy, and we have, actually there are like libraries of reactions that people have done. Either they did the reaction and they measured delta H, or they used other computational measurements to determine what delta H is for that reaction. And that amount of heat that's produced, that enthalpy, is for the stoichiometric quantities in that reaction. We were talking about this on Monday. So if you have 1 mole of propane that reacts in this chemical reaction, you would get 2,044 kilojoules of heat, or enthalpy heat transferred. If you react 5 moles of oxygen, say we also would produce 2,044 kilojoules of heat. And in both of these cases, we're assuming that, like in the case of the propane, there's enough oxygen around to do that reaction. And in the case of the oxygen, that we have enough propane to do that reaction also. We can't just react oxygen by itself. For those stoichiometric quantities, again, we could use this delta H and create a sort of mole ratio, like we did when converting from maybe moles of oxygen to moles of CO2, or propane to water. So this is like a simplified version of that, where you had this fake equation, but 2 moles of A would give us 1 mole of AA. So in that reaction, we produce negative 51.0 joules of heat. And so the question is, how much heat would be associated with the reaction of 6 moles? And this is where my brain started to crash on Monday, and I ended up doing a bunch of math wrong, but we got it correct in the end. So this ratio here, the negative 51.0 joules to 2 moles of A, is just from this balanced chemical equation. So I said this is 2 moles of A, we produce negative 51.0 joules of heat. And so we can set that up in this equation to cancel out moles of A and give us joules of heat produced. Now, how do I know this is joules of heat produced and not joules of heat absorbed? Because it's negative. So if this is a negative value, that means that is heat leaving the reaction. Or you can think of heat like money. It's spending that money. It loses that 153 joules. Okay. We did one of these as a sort of real chemical reaction. But the question is basically the same. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. And ultimately, this is a stoichiometry problem. And what's the first step for basically any stoichiometry problem? You do have to have a balanced chemical equation. But when you're looking at your initial values, you want to calculate something first. Moles. So if you're not given moles, and we were given grams, we had to figure out some way to put that into moles. Now at this point, we actually have a few ways to do that. This is to just go way back. Remember that time before spring break? So long ago? We can calculate moles from grams. We can calculate moles from solution volume and concentration, molarity. Or, yeah, we covered gas laws. So we can use gas laws too to figure out what a number of moles might be for a reaction. So we could have been given this amount of ammonia in liters of ammonia, and then given a temperature and pressure, and we could calculate moles from that also. Regardless, it's a stoichiometry problem, so we're looking for moles first. And why are we looking for moles first? Not because of the limiting reactant. Yeah, basically, right? The ratios in here are moles. So I can't take my number in grams and plug it in or use any of these mole ratios because they're in moles. So we got to get to moles so that we can relate everything back to our balanced chemical equation. And you can see that the units work out when we do that. So 155 grams of ammonia. This is the molar mass of ammonia, which gets us to moles. And then using the ratio of 4 moles of ammonia to negative 600 or 906 kilojoules of heat, you say or I should say, for every 4 moles of ammonia reacted, 906 kilojoules of heat ultimately ends up being negative 2,059 kilojoules. The only way that this differs from a regular stoichiometry problem is that we're using this delta H value, which is kilojoules per whatever coefficient in the balanced chemical equation. The other way that it might differ is if we do this in the sort of opposite direction. So what mass of butane in grams is necessary to produce 1.5 times 10 to the 3 kilojoules of heat? I guess ultimately the first step ends up being the same. How do I relate kilojoules to moles? Yeah, because this, and maybe I should have done this on a previous slide, but we can take this, we draw up a bunch of different ratios. It's like negative 2,658 kilojoules, or do it like this, per how many moles of, that's what do we want, the butane first. So if I look at my chemical equation, that's, here there's no coefficient, meaning 1. So negative 2,658 kilojoules per 1 mole of butane, which is the C4H10, to make it 1 mole of butane. A lot of the times you will see this in these, again, right, somebody either did calculations or they did this reaction, and most of the time we're not concerned about the amount of oxygen, because 21% of the atmosphere is oxygen, but what you're more concerned about is like how much butane would I be burning? So to make this per 1 mole of butane, it's all divided by 2 so that we get that coefficient of 1. But that doesn't mean that we can't use still the 13/2, as weird as it feels. So just writing out more of these ratios, right? We do negative 2,658 kilojoules per 13/2 moles of oxygen. Improper fraction though, maybe. We could rewrite it as 6.5 if you wanted. So what's another ratio that I could write up? Yeah. For 4 moles of CO2. And this is a little bit beside the point to solving the problem, but just to show we can relate this number to all of these. And so if I wanted to know for water, 2,658 kilojoules, 5 moles of water. So those are all possible options. Now, which one do we care about here? Yeah, the C4H10 first and the CO2 eventually. It's asking us about 2 here, right? What mass of butane? Here, write that above it too. C4H10. So we'll do that one first. And again, like I said, the first thing we need to do in a stoichiometry problem is get to moles. So if I've been given 1.5 times 10 to the 3 kilojoules of heat, I can relate that to not moles of heat or anything, but I can relate it to the moles of butane. And so can't use this in this form, but if I flip it, then I get negative 2,658 kilojoules of heat, 1 mole of C4H10. All right, there's something I forgot to take into account. Yeah. So this says producing this much heat. There's no such thing as negative energy, but we can talk about a negative flow of energy, meaning energy flowing away or energy flowing to, right? If I have energy, or if this reaction is producing heat energy or producing thermal energy, that's flowing away from it, which means that this is a negative 1.5 times 10 to the 3. Okay, and then I think from there, there's only one more step. Yeah, molar mass of butane. So molar mass 58. Oh, that's right, it doesn't show up there. Okay. So just multiply by the molar mass. So negative 1.5 times 58.14 divided by negative 2,658. 0.0328. I guess just 2 sig figs. 3. I did just 1.5. little bit smaller. No, this is positive 3. How long can I blame jet lag? I've heard it's 1 day for every hour of jet lag, so it feels like I've got 16 days. All right. At least this week. God, just... I know it's on the page. We'll get through this, because I know it affects you guys too. Okay. So what changes if I want to do this for CO2? Yeah, I just need different mole ratio for CO2, as I wrote all these out. We could have done any of these, but we'll change this 1 to a 4, so same amount of heat. And then we need the molar mass of CO2. Let's see if I can type it right this time. Good. Yeah. Any questions about that? Practice is the best for these kinds of things. Yeah. Yeah. So I would reduce the fraction to a decimal. So take 13 and divide it by 2. You'll get 6.5, 6.5. Yeah. So you would change this 4 to 6.5, and then this would be O2, and then you would use the molar mass of oxygen. Yes. And actually, that kind of gets into the next thing. We're talking about Hess's law. If I multiply all of these, ow, funny bone, tweaked a nerve. When you multiply all of these coefficients by 2, you also multiply this value by 2. Because if I'm multiplying twice as, or if I'm reacting twice as many things, I will get twice as much heat. So you can multiply all those by 2 and not have it with the improper fractions. This delta H, though, then also has to be multiplied by 2 because it's part of the reaction. It's because of the wording of this problem. So what does it say about the 1.5 kilojoules of heat produced? So produced meaning that the heat is coming off of or leaving the reaction, which means that this would be a negative delta H, or yeah, negative delta H for our particular reaction because it's exothermic. So if this reaction instead said, what mass of butane in grams would cause some amount to be absorbed, it's really weird. But if it said absorbed or was, can't think of another word for absorbed right now, anything that hints at heat is going into the reaction or that it's sucking up heat from its surroundings, that would be an endothermic reaction. Then we would leave this positive. But if I left this positive in this problem, I still have this negative 2,658 kilojoules, which is the delta H. And so then I end up calculating a negative grams, which doesn't make sense. You can't have negative mass. Okay. We're unfortunately going to skip over those to talk about Hess's law, so some other relationships here. And actually, like that question asked earlier, what happens if I multiply by 2? We change it and we really treat it just like one of the coefficients for the most part, except delta H depends on the direction of the reaction. So if I multiply everything by 2, then delta H also gets multiplied by 2. And like I just said, this depends on the flow, right? So in the forward reaction, for our heat reaction up here, or burning of butane, this produces this much heat. But if I could somehow make this reaction go in the opposite direction and go from water and CO2 back into oxygen and butane, that would absorb heat in the reverse direction. You think it is, I guess, in that sense, going back in time. So if I take a reaction like this one, so we have this A plus 2B goes and produces C, has some delta H1. I can take that reaction and I can make my products reactants instead, and my reactants products. So now I've got C becomes A plus 2B. So it's the same thing, now it's just the opposite direction. And when that happens, delta H, so delta H2, so really the 2 here is just saying after we transformed it, it's the negative of delta H of the original reaction. So for the butane reaction, it'd be like if I wrote the butane reaction as 4O2, 4CO2. Now I've got CO2 and oxygen coming together to be butane and, it's supposed to be H2O. CO2 and water, sorry, becoming oxygen and butane. This is now positive. So you flip the reaction, you flip the sign. And these are manipulations that we're going to use to be able to calculate the delta H, I guess a theoretical delta H of different reactions, is related to what you guys did in lab this week. So Hess's law basically says we can calculate a delta H of a different reaction if I know the delta H for 2 separate reactions. I can add those together. So adding the A plus 2B forms C. And then if C turns into 2D, the combination of those 2 reactions is just their enthalpies added together. And really, that's another step here. You do it like this. Since C is on both sides of the reaction there, it's just spectator ions, where if they're the same on both sides, we cancel them out. Because when I add these 2 together, this would have been, before simplifying, A plus 2B plus C goes to C plus 2D. But since C is on both sides, we can cancel that. C is equal to 2D, substituted in. That works really well for this one, but when things get a little bit more complicated, it's not quite as simple. But that's the basic idea. If I can get C on both sides, I can cancel it out. And again, this works because delta H is a state function, meaning that if I was able to do this reaction, I should get some enthalpy of delta H3 here. Or if I do each of these reactions separately and I measure what their delta H is, I could just add those together and I should get the same delta H as doing this reaction, which is what you guys did, or what was the theory behind what you guys were doing for the Hess's Law lab this week, that you did one reaction that was the full thing, and you measured that delta H, or you measured the temperature so you could calculate delta H. And then you did the reaction in 2 parts, and then calculate the delta H of each of those, add those together, and it should be equal to your other reaction. So this is useful for doing things in theory. If I want to know maybe if a reaction is going to be really exothermic, I could do smaller reactions to figure out what their delta H's are, to figure out how exothermic the reaction I want to do is going to be. All right. Again, why is this useful? Because we can do it without actually measuring it in the lab, and also, I should say too, without even doing any experiments, there are tables of these values for different reactions that already exist. Other chemists have done the research, they did the science, figured out what those delta H's were, and then published them. And then they get put into lists. So you don't even need to do a reaction at all. You can just look it up. Now, of course, there's other things that can go in that would change that delta H, or whether a reaction would actually happen or not. But the way that we're going to use this is to basically manipulate reactions with known delta H's, like you would get from one of those tables, to calculate it, to get the delta H for some reaction of interest. I really like these because they're very puzzle-like. Okay, yeah. And we're basically just going to do 3 things with these reactions. We're either going to multiply it by some coefficient, like we did, or like we talked about, I should say. Multiplying by 2 would double the delta H. Or we're going to, actually, yeah, we're really only doing 2 things. We're going to multiply it by some coefficient, or we're going to flip it. So you're either going to multiply, or you're going to change the sign of delta H, positive or negative. So we're given here the delta H of a reaction. And one of the keys here is just spotting the difference between the reaction that we have and the reaction that we want. Right? So how is 2A plus B equals C, my original reaction, different from the new reaction that I want the delta H for. Times 2, and it's flipped. Yeah, so my product, or my reactants in the first reaction are products in the second reaction. So you can do this in 2 steps. I'll flip it first. It doesn't matter what you do first. So I'll have C. It doesn't matter if you do these in 1 step or 2. And so now the delta H is going to be negative 122. But like you guys said, we need to multiply this, C to 2A plus B. We need to multiply that by 2 now. And that'll give us 2C goes to 4A plus 2B. And so my delta H also gets multiplied by 2, and so there should be negative 244 joules. So that would be the answer. That's the simplest version of this. How do I take one thing and do a couple manipulations to get a new one? Are there any questions about that kind of thing? No. Could be anything. Could be, I should say, any integer. Although you might even be able to do fractions, and we saw you get a fraction, but yeah, like how do I get my coefficients for my original reaction to match the coefficients in the new reaction? Or the next level of this is taking multiple reactions and trying to end up with some other reaction. And this is, again, another place where it's, okay, how are these different? I think one strategy that's really helpful is to look at the reaction that I want and figure out where those are in my sort of given reactions. So I might start with, okay, my final reaction needs to have NO2, or N2O, sorry, dinitrogen monoxide, and it needs to be a reactant. But I can go over to my other reactions here. Let's find, okay, dinitrogen monoxide is only in that last one. The other thing to note is it's already a reactant there. So I'm probably not going to be flipping that reaction. The other thing we're looking for is nitrogen dioxide. So nitrogen dioxide is a reactant, or I want it to be a reactant to my final product. And which of my 3 reactions has nitrogen dioxide? The first one, but it's a product. Now, none of the other ones have it, so what does it tell me I need to do to the first reaction? Got to flip it, right? If I flip it, that means nitrogen dioxide will be a reactant and the other things will be products. So we're going to have to change the sign or multiply by -1 and flip that one. And then the last one we look at here is just scribble over that. Nitrogen monoxide. And nitrogen monoxide, where is that in my 3 reactions? It's a product in my second one, but it's a reactant in the first one also. So if I added these together the way they are right now, it would just cancel out. That's not what we want. So now I'm going to take this first one. I'm crossing it out because I'm going to write it below. I think it also helps if you do line up the reaction arrows. This will be 2 and O. Give it a little more space. Plus O2. Okay, and that's going to be a delta H of a positive 113.1 kilojoules. Okay, so now we've got sort of everything. If we added these together, we'd have all of the things we want on the correct sides. But we also have a lot of other stuff. We have other things that we don't want. And we need to consider the coefficients of the things in our products, or in our final reaction, right? So our coefficient for dinitrogen monoxide, that should be 1. The coefficient in nitrogen dioxide should be 1, and the coefficient for nitrogen monoxide should be 3. As is right now, I'm going to end up with 2 N2O, 2 NO2, and 4 nitrogen monoxide. So what should I do? Or I guess, how can we guide like our further decision making from here? Subtract something? Because we can't really just like, subtract something from it, but you mean like, multiply it by a coefficient? I think it would be valid to here to multiply by a half maybe. But the other thing is, even though our final reaction here, right now it's 3, 1, and 1, it could be 6, 2, and 2, and then reduces. And that might be a good way to go because this is 2, that's 2, so those are going to be 4, which is already more than the 3. So I would have to multiply by some fraction to make it smaller. The other thing we could do is, if we look at what else is in here that we don't want. We've got these nitrogen and oxygens that aren't present in the final reaction. Now, they're already on opposite sides. So I got nitrogen in the reactants, I got nitrogen in the products, we got oxygen in reactants, oxygen in the products, but they're not going to cancel out. Right? Because I got 2 nitrogens here, but there's only 1 nitrogen there. I need that to be 2 also. So if I multiply that one by 2. So I'm going to do it like this again, and I'm going to cross it out. But we're going to multiply that by 2. So this will be 2O2, 2N2, goes to 4, and O. Again, that's the one we want to keep. Okay, so now does my nitrogen and oxygen cancel out? Maybe I can... Oh, did I do that wrong? I didn't do it right. Yeah, they should cancel out now. I know this is a little bit busy, and I'll bring it back at the end, but for now, let's just hide that other stuff so we can focus on this, but I need this. Because this delta H now is going to be multiplied by 2. Oh gosh. 365.2. Yeah. Okay. Yeah, so I've got 2 nitrogens there. This will be 2 nitrogens. So those will cancel. And then if I look at the oxygens, there's 2 here, but there's 1 oxygen here, 1 oxygen there. When those added together, that'll be 2. So those will also cancel out. And then when I add these together, this will be 2 N2O plus 2 NO2 forms 6 NO. Like I said, now I can look at this, say 2, 2, and 6, all divisible by 2. So when I simplify, divide that by 3, and actually maybe we should do this in steps. Because once we're at this point, we can add, just like we add these reactions together, we add the delta H's together. Negative 163.2 plus 113.1 plus 365.2. Because this is the delta H for this reaction where we've got the 2, 2, and the 6. But if I reduce this equation by dividing everything by 2, that means I also have to divide my delta H by 2. So then, or same as multiplying by a half. So my final delta H will be 157.6. Sorry, say that one more time. Yeah, yeah. And it's like try to do one thing focus on one thing at a time. So like we started out by saying, okay, I want these 3 things and I want them on those sides. So I go and I look at my reactions that I'm trying to combine together, And we do the flipping first to make sure everything's going to be on the right sides first. After that, we can look at the coefficients and either say, I need this to be a coefficient of 3, 1, and 1, or I look at the other things that were in here, like the nitrogen and oxygen, that aren't in my final reaction, and say, I need to cancel those out, so how do I cancel them out? I guess just because of a property of the way these problems are, by canceling those things out, I automatically ended up with the correct coefficients after I simplified. Any other questions there? And it really does help. Go step by step. Make sure that you're always rewriting out your delta H and that you're taking into account the manipulations that you do to those delta H's. This is one of those things, if you are doing this like on an iPad or something where it's really easy to erase stuff, try not to erase things and replace them with numbers, because then you lose the fact, oh, I did something to this and that changed that number. You don't have any sort of record of having done that anymore. And also just rewrite them. Doesn't take that much longer, but it is a little bit cleaner, especially when you have to flip them. Okay, so let's do one more of those. We have one more, and then we can talk about standard enthalpies of formation, and then might end up changing Alex. Yeah. Okay, this is the same type of problem. We're given reactions, and we're told to, or asked to find the delta H for a given reaction. How do we start? It's a lot of information. Yeah, and usually we can look at just, not just the fact that there's 6 here, the fact that there's 3 H2s. Yeah, either way. So what's the issue? If I want to have the right number of hydrogens, how do I get to 3 hydrogens? Yeah, but I can't multiply. I guess we could think about multiplying this one, but yeah, multiply this one by 3, but then that would make that 6, which could be fine. We could end up simplifying to something. Yeah, so we could do that. Let's multiply by 3. This is another one of those types of problems where there's not a single way to solve it, but there is one final right answer. I guess the solution of this problem is also a state function. Doesn't matter how many steps you take to get there, the final answer will be the same. Here you can use a fraction. Yeah, so what I was saying earlier, if instead of multiplying by 3, we multiply by 3/2, which is a little bit weird, and then when we try to add these together, it's going to be weird. So it might be easier to instead take this one and also multiply it by 2 temporarily. So we're looking for 6, 2, and 6. Because now that would match, because this will be 6, and I'll rewrite that one. Yeah, we'll have to multiply the next one also. Sorry. Oh, and then delta H will be negative 43.6 times 3. Okay, cool. So now we'll have the right number of hydrogens to match with our multiplied one. And right, by multiplying this also, we can also just come back and simplify it at the end. Okay, yeah. So I've got the right number of hydrogens, got the right number of oxygens. Is O2 in my final reaction? No. But O3 is, and O3 is a reactant, but in my reaction, O3 is a product. So that one we got to flip, and there's also another thing that we have to do to it. Is there? No? Actually, no, it might be fine. I think we just have to flip it. So we'll flip that one, multiply it by -1. So this will be 2O3, 3O2. It's delta H, 285.4. Crossing things out with one line is always nice, because then if you regret crossing that thing out, you can still read it, rather than erasing or scribbling or something else. All right, so now is everything going to cancel out to give us the equation that we want? Yeah. because the only thing we wanted to get rid of was the O2. And there's in the reactants, there's in the products. So this will be 6H2 plus 2O3 gives me 6 H2O will again be the sum. So it's always going to be adding them together. So make sure you include negative signs. This will be negative 1450.8 plus negative 285.4. So as we did it, this is going to be negative 1,736.2 kilojoules. Is that the final answer? Because now, after getting rid of that, we can look at this and say, ah, yes. Remember, we multiplied this by 2, so that it made it a little bit easier to know we're looking for 6, 2, and 6. But 6, 2, and 6, divisible by 2. So take everything, divide by 2, and we really only need the delta H, so we can divide that by 2. Cool. Okay. So that's Hess's law. And if, I mean, you can use the Alex to practice, but like during the week, if you're like in the middle of a module, you can't go back and do those. There are going to be practice problems in the book, and the book also has the solutions at the back of the book. So at the very least, you could look there for more practice problems, because I think that helps the most with these Hess's law problems. Getting used to spotting, okay, what differences am I looking for? And then the manipulations are easy, right? If I flip it, just change the sign to negative. If I multiply by 2, I mean, the math is not that complicated. It's shuffling things around that takes a little practice. Okay, so another extension of this that I did want to touch on, these standard enthalpies of formation. So we can have experimentally measured using calorimetry for delta H, or inferentially through Hess's law. But we have these other things called standard enthalpies of formation. There's a defined 0, and then we're measuring everything else from that defined 0. And so the defined 0 is usually defined as the standard state of things. So if we can talk about stuff in sort of these relative terms, we can have delta H's for formations of specific compounds from their elements. So the standard state, different from standard temperature and pressure. The standard state of a substance depends on what that substance is. For gases, it's exactly 1 atmosphere of pressure of that gas by itself. For liquids or solids, again, 1 atmosphere of pressure and temperature of 25 degrees C. Does anybody know why 25 degrees C? It's actually a really simple reason. It's a little bit warmer than room temperature, because it's really easy to warm things up a little bit. It's a lot harder to cool things down. So you could put something on a hot plate on a very gentle heat and get it right up to 25, but you'd have to have a whole refrigeration unit if you wanted to cool it down to, say, 0 degrees C. So in a lot of cases, 25 degrees C is just above room temperature. And then if you've got something in solution, then that's exactly 1 molar of that solution. So really they tried to pick, in the case of temperature, a convenient temperature, easy to do in a lab. And then for everything else, pressure is 1 atmosphere, concentration is 1 molar. Make the numbers as simple as possible. If you get to define things, then make them simple. So the difference between regular enthalpies, a standard enthalpy uses this naught, or this little superscript 0, and that's the enthalpy change when everything's in its standard state. Again, those values that I told you about previously. And then a standard enthalpy of formation is the reaction forming 1 mole of any pure compound from its constituent elements. So forming CO2 from pure carbon and pure oxygen. And then those elements have to be in their standard states. So in a lot of times, these are theoretical. And this works because for a pure element in its standard state, the delta H of formation is 0. So what's the delta H of formation of O2 at 1 atmosphere in the gas phase? Be 0 kilojoules per mole. That's its standard state. But when we combine those into different things, that's when we get enthalpies, because we're changing them away from the standard state. So you end up with tables like this. Got a bunch of delta H standard enthalpies of formation for different compounds. And you can look these up. This is a very truncated or shortened table. And for each of these, so actually if I go back up here, I think CH4 should be on here. Yeah, so CH4 is over here. That's negative 74.6 kilojoules per mole of methane forming. Now, there's a chemical equation behind that, and that's to make CH4 from its most basic elements in their standard states. That would be carbon, and sometimes there's specific allotropes. So specifically, the graphite form of carbon as a solid, plus two H2 molecules, which is its standard state, so we've got to be at 1 atmosphere, to form CH4 gives us this delta H of formation. So that's useful because now I have this whole table of different compounds. We know about Hess's law. We can take these delta H's and we can flip things. We can add reactions together. And so we can use standard enthalpies of formation to figure out a theoretical delta H for anything that we might want to make. And all we got to do is find the compound we want to make on the table, or find compounds that we need off the table and add their chemical reactions together like we did on those previous examples. And then everything's in kilojoules per mole. And then for any of those compounds on that table, again, like carbon and oxygen, it's going to be carbon in its solid graphite form, oxygen gives carbon monoxide, or we could do carbon dioxide and solid graphite. Oh, wait, I think this is supposed to be a half. Oh, yeah, it is a half. Good. The typo up there, right? So then we just use, because this is always, for these enthalpies of formation, it's always per 1 mole of whatever you're making. Again, we end up with these weird fractions. So it's 1/2 oxygen to make that CO. And so you can find those all in tables. As another example, we could take enthalpy formation of sodium chloride. And really, if we're doing just a single compound like this, we go and we find it on the table. So NaCl solid. Sometimes you'll have different forms. Just to highlight here, the enthalpy of formation for water as a gas is different from that as water as a liquid. So you got to make sure you take that into account. And we're looking for NaCl. So its enthalpy of formation is negative 411.2. So the delta H of formation, 411.2 kilojoules per mole. And you could probably take a guess. What would the standard state of sodium be? Oh, the enthalpy of formation for sodium would be 0, but what is its standard state? Is it going to be a solid, liquid, or gas? Solid. Sodium's a metal. And it's a solid at room temperature. There's only one, I guess not even, one liquid metal that's mercury at room temperature. So this would be Na solid. What about chlorine? What would its standard state form be? Solid, liquid, or gas? It's gas. And it's Cl2. So that would be the equation for the standard enthalpy of formation for NaCl. Actually, is this? And then if we do lead nitrate, what was going to have lead nitrate? Did I miss it? So we'd find lead. It's not on that table. Lead nitrate. Solid, negative 451.9. So delta H of formation, it's up there, 451.9. And this is to make PbNO3 2 solid. Okay, so what would be the elemental forms, the standard state forms of the things to make lead nitrate? Lead. So these are all, everything that goes into this is going to be like lead in its standard state form, which means as an element, basically off the periodic table, lead solid, What other element is in there? Nitrogen. Oh, and actually, I should have put a half there. Nitrogen, though, is going to be N2. And then oxygen, O2. And then we need the correct coefficients for those to make 1 mole of lead nitrate. So what coefficients do I need? Yeah, lead's going to be 1. Nitrogen's going to be 1 because there's 2 there. And then I've got 2 nitrates here, so I need 2 of those. But I need 6 oxygens. So this will have coefficient of 3. Then in theory, we could take this and say, because oxygen's standard state form would be O2. So the standard states are almost always their elemental form. So oxygen as an element is O2. If we put it as O3, then we'd have to look up ozone. I don't know if it's in this list. Oh, ozone. But then ozone even has its own enthalpy of formation, while O2 would be 0. So basically, you find the delta H of formation value from a table. Whatever the delta H of formation that you're looking for is the product. And then the reactions that go into that are the elemental forms of all of the elements. And it doesn't matter for these, it doesn't matter that this is nitrate, it's still nitrogens and oxygens. And so the delta H of formation is from nitrogen and oxygen. Okay, I think that's as far as we're gonna get, yeah. This is the kind of thing that you could do if you look up all these delta H's of formation. You can add them up together and find the delta H for a completely different reaction.